Okay. In your slide, so do you see my stick, brown stick there? No. Or you just see my cursor?
Just
Just the cursor.
cursor.
Cursor. Okay. Last time, okay. So I mean, I need to change into the. I stop presenting, so I present the entire screen. Okay. Now you could see my stick with hand there.
Yes, yes.
Yes.
Okay. Okay. So now because we have two axes, so one is Cartesian coordinate, and just now I show you the Navier-Stokes equation and the continuity equation in Cartesian, and that's actually the simple one because we only have x, y, and z. So and then we are going to derive the continuity equation for cylindrical or polar coordinates. So it's quite a little bit tough because we have a three axis which is not similar like Cartesian. So for cylindrical coordinates or polar coordinates, so we have r axis like this, and then we have the theta axis. Okay, because I already explained it previously, and then at the same time we have the z axis, mean the thickness of the molecule. Okay. Okay. So, for example, for this situation, okay, previously in Cartesian coordinate, we will take cube to express to become the smallest size of the fluid, and for polar coordinates, we will take our control volume here is actually something like this. So it is actually a part of a circular shape. So it's sometimes we assume that there is one molecule here, and this molecule rotate at certain speed, and the location of this molecule can be determined by the length of the radius, and also the location can be determined by its angle. So and then for sure molecule and this fluid flow has thickness, mean the height of the cylinder might be. So then we have the z direction like this. So mean let's say our molecule here, so the coordinate is the value of r, and the angle theta here, and also the z direction. So you could see that the three axes for polar coordinates is quite unique compared to the Cartesian coordinates. So the molecule here is actually located like this. Okay, so now this is the axis of r, and this is the axis of theta, and this will become the axis of z. So because this is a small portion of the total fluid for this one, so we could say that the length of this one is delta r. So the length here is delta theta, and the length here is actually delta z. And for polar coordinate, we will use the symbol of velocity with a subscript like this. So for v or u theta means the velocity parallel to the angle here, and vz is the velocity along the z-axis, and vr is the velocity for the r radial direction. So the idea is still the same. We are using the idea of mass flow rate for inlet minus mass flow rate at outlet equal to changes of mass inside the system. So m dot is the mass flow rate. So the equation will become rho a v, and the v is actually the velocity of the fluid. Okay, so because we have three axes, and we are going to derive it into three elements, so I will do it part by part. So you know that in Cartesian coordinates, so we have three inlet and three outlet. So it is the same for the polar coordinates. We have also three inlet and three outlet. So now we are derived for the R axis. So mean this is the R direction. So we just assume that we have inlet here and outlet here. Mean the velocity is parallel on the R axis. So the idea of m mass flow rate in minus m flow rate out. So we could calculate that. So mass flow rate in will become rho AV, and we know the V, the A is r d theta, actually the length of this one times dz. So we have r d theta dz as the A, and the velocity is Vr, and the rho is the density. And the outlet here, so the A is, okay, the area of this one, so the length of this one is r plus dr times d theta. So we have r plus dr d theta as the area here. As r plus dr d theta will become the length of this one, and then the height of this one is remain as dz. So in this calculation, we found that the length here is a little bit longer compared to the length here. That's why we are not using r d theta dz. So we are taking the whole idea here, and dz is the thickness. And again here we are using rho Vr plus del R rho Vr dr, because we are analyzed on R axis. And the idea is the same, because we believe that sometimes density will change, sometimes velocity will change, and might be both of these parameters change at the same time. So we are using the partial differential here. So and then if you you expand everything here, you could write like this one, and again and then we could neglect the small value. So normally people will neglect dr times dr because we have here. So we could assume that this will become equal to 0. So it is too small, and then we neglect the calculation. So if you do this, you will find that the m inlet minus m outlet will have this term. So we have dr, d theta, and dz. So it will reflect the volume of the cube here. So and then again, we do the same things. Now we are analyzing the z-axis. So z-axis is the vertical axis like this. So the m inlet, you could see that it is r d theta times r. So we have the r d theta, and then we multiply with the r here, and then we have the cross-sectional area for the top and the bottom here. So we assume the flow is from the top, from the bottom to the top. So and then we remain use the same cross-sectional area here, because according to this diagram, the cross-sectional area is remain constant. So it's still the same area. So if you solve this one, you will get this term. And then for v theta, so this means the flow will come from here and will go out at this area outside there. I think you could calculate here dz dr, mean dz is the height of the one, this one, and dr is the length of this one. So this is the area, dz dr is the area. So and then another is the velocity and the rho. If you simplify this one, you will get this term. Okay, then we are going to define what is dm over dt. So again, mass is actually rho times volume. So we calculate the volume of this one. So for this one, it is okay for us to just simplify the calculation of the volume. As I said, we know that the length here is longer compared to the length at this one, but we just assume it is not so much different. That's why we only take the simplified version of volume here with r d theta dr dz. And then we substitute the value here. So we could say that dm over dt is d dt rho r d theta dr dz. And this is the common equation for the continuity equation. So we substitute all of these, and then because all the terms here has d theta dr dz, so I think we divide all the terms here with d theta dr dz. So finally we could have this one. So and then again here, so we have del dt over rho and r. So it will become rho dr dt plus r d rho dt. So and then here, I hope you could understand the idea of dx over dy. So it means the meaning is the changes of x compared to y or along the y-axis. Okay, and then for dr dt here, we could say that it is equal to 0 because the radius is not going to change regarding to the time. So means that the rdt is 0, and then means we could neglect this one. We could bring these terms into the left hand side, and then we could equal all of the equation into 0. So then if you do this, you expand this calculation, so finally you will get this one. So this is the compressible equation of continuity in cylindrical polar coordinates. So why we call it compressible? Because it's suitable for compressible and also for incompressible. But for incompressible, so for incompressible, we will assume the value of density is equal to 0. So then we could simplify this equation more. But before you simplify that, you need to expand the volume, the calculation of this one, because this is the partial derivation. So you need to expand it, and then you need to neglect the value of rho. Okay, and then please try to do this at home, because it just a simple calculation, I think. So you could have this term. Okay, now, okay, this is just to for incompressible, because there are no changes in density and velocity for z direction. Okay, and there is no changes in density, and the velocity for z direction is also equal to 0. So the continuity will become can be expand like this. We neglect certain parameter, and finally we could write like this one. So because we don't have, sometimes in certain textbooks, they will not use the VR and V theta. Might be they use U theta and UR. And some textbook, they will use the word, the symbol of dash. U dash is for the R axis, and UV is for the U dash is for R axis, and V dash is in theta axis. So this is just the way people express the value. So the most important things is, I hope you could do the derivation of continuity equation here. So then this is the continuity equation for Cartesian coordinates, and this is the continuity equation for polar coordinates. And then for Navier-Stokes equation, so we skip about the derivation. So because it's the idea is the same actually, but we need to deal with 3 axes. We cannot simplify it because the axis is not always the same. The nature is r, theta, and z. So I just skip that. So, but I give you the Navier-Stokes equation for cylindrical coordinates, for polar coordinates. So again, and it is totally different. Please think that it is totally different compared to the compared to the Cartesian coordinates, because the similarity is almost zero. So means, yeah, you cannot use the idea of Cartesian coordinate to write the polar coordinates. So you need totally to remember different equation. Okay, so this is the symbol for dt for the capital 1. Okay, and then this is the meaning for nabla square. Okay, because okay, and this is the equation for Navier-Stokes equation for r axis. Okay, all of this, and then so this is for theta axis, and this is for the z axis. Okay, and sometimes, okay, I already upload these notes in my website. Okay, so you could have that. Okay, I will change one mistake there in previous notes. So what I want to say is sometimes because it is too much 1 over r here and sometimes 1 over r square and so on and so forth. Please take note about the conversion of this one, because in certain textbooks they will write 1 over r del r du z del r. Okay, and in certain textbook they will write in this term 1 over r del du square dr plus and so on and so forth. So and it's if you're not expanding by yourself and see the difference, you will might be cannot relate why this term can turn into this one. So so I hope you could do a little bit the calculation of this, the proof of this equation. So because in some time, or another terms is sometimes, for example, 1 over r del dr. So you will find in somewhere, for example, in here might be, I will see that one. Oh no, that dr. So okay, take your time. If you see this term in some textbook, they will write this one. Okay, so means that okay, so it's equal with the above one. So please take some times to see, or to at least try to remember the Navier-Stokes equation for the polar coordinates. So and then there are no I would like to say here, some for me there are no relationship between the z, the theta, and the r axis, because if you see here, it's some parameter here is actually not exist in theta and not exist in z axis. So means it is not like a Cartesian coordinate, which the pattern of the equation is almost the same. For polar coordinates, it has a totally different arrangement of equation. So is that okay for this note?
Okay.
Okay, so we just break for about 5 minutes and then we continue. The usage first the another continuity of the about this equation, and then we try to comes out with the idea of ideal flow, because in our textbook they're talking about flow around cylinder and so on and so forth. So I try to give you some basic ideas about flow in cylinder. Okay, so we break for a while, for about 5 minutes. Okay, assalamualaikum and good afternoon. So is that okay? Everybody's here?
وعليكم السلام
عليكم
ورحمة الله
السلام يا
وبركاته.
دكتور.
Okay.
Yes, okay.
So now we are going to refresh your what you learned previously. So about the idea of string function and psi and so on and so forth, because we need to know the equation that show about the fluid flow. Then we could analyze them by using the changes of velocity. Okay, the idea because if you see the Navier-Stokes equation or the continuity equation, it will give you a lot of parameter about velocity. So we have u, we have v, and sometimes we have for polar coordinates, so we have u theta, u r, and u z. So means that they will manipulate, they will calculate everything based on the velocity. But how we could get the velocity and we could make sure that that velocity is actually the truth one, the correct one. Okay, that's why it's then the research continues and it finds that we need to start with the idea of stream function. The stream function is actually the equation. You know, the function here means the equation to describe about how the fluid flow on certain object. So in stream function will be used especially in simulation, okay? And it will the symbol is something like this, and it called psi. Okay, the way you write this symbol is actually you just write the simple one is something like this. Okay, so you could have psi here, and this is psi. So in common fluid mechanics, the psi here is actually reflect the stream function, the continuity equation, the flow rate Q. And I think this is the common equation that you already know about how to calculate a flow rate in fluid mechanics. You need, so the equation is Q equal A times V, which is A here is the cross-sectional area and V here is the velocity of flow. And again, because the equation in continuity equation that we learned previously is in velocity terms, and also the polar coordinate is also in velocity terms, so means we try to do something with the psi here, with the flow rate here, based on the velocity. So means the idea is velocity is equal to flow rates divided by its area. Then we could simplify like this. Okay, for example, again, so this is the particle that we learn in that we use in Cartesian coordinates. So we know that the velocity for the x-axis is u and the velocity for the y-axis is v, and then the molecule here is dx and dy. So we could, because we assume that psi here is the flow rate. So we could say that the velocity here is u, and then it can be written that u here is equal to d psi over dy. So d psi here means the small parts of the flow rate that flow into this area divided by the y. So y here is actually the cross-sectional area, means the height here is y and we have a width here is z, for example. So it's actually dy over dz. Okay. However, for this calculation, we assume that the width here is equal to 1. So and then it will become dy times 1. So and then you never see the numbers 1 here. So that's the symbol. And the second one is, this is the common calculation because it is only for 2D. So and then for V here, the velocity of V here, so is equal to d psi, means the flow rate that flow for this cross-sectional area divided by its cross-sectional area, which is dx times 1 unit of width. Okay, why we put a negative here? It is because after this, we will see the polar coordinates. And polar coordinates will rotate from, it will rotate like counterclockwise or clockwise. So means that the to differentiate between the counterclockwise and counterclockwise and clockwise direction. So we assume that everything that counterclockwise that move from the bottom to the top will give the negative sign. So mean because the V here, it push the molecule, and if in rotation, so it will push and makes the cube here rotate counterclockwise like this. So means that the direction of this one is equal to negative sign. So actually the negative sign is come from the negative V here. So and then we bring it to the right hand side. So again, and then for the polar coordinate, we are using the same ideas. So UR here is the velocity on the r-axis, and then we could say that dr is equal d psi over r d theta. So it will become, because the r d theta is the length of this one, and the width is equal to 1 unit. So it's remain as r d theta. And u theta is the velocity for this direction. So and then we could say that because it's rotate in counterclockwise, so then we could write it is a negative d psi over dr. So dr here is the length of this one, and it times 1 the width of this particle. Okay, and then both here is negative. Please make sure that you write negative here, because this is the way we put the difference between clockwise and counterclockwise. And again, all of these is actually done on your computer. So that's why the negative and positive sign is very important, because the calculation is very specific about the sign. Okay, so what is psi actually? So psi is actually the streamline. So the streamline is the simple one, is if you want to design a car to prove that that car is in streamline shape, or it has a very small in term of drag force and lift force. So what you do is you just use smoke generator. You just use a wind tunnel, and then you can create streamline like this. So means that if you simulate this situation in your computer, every line of this smoke must be present in equation, in mathematical equation. Everything here has its own mathematical equation. So that mathematical equation is actually the stream function. So stream function, stream means the streamline, function mean equation. So that's why we need to come with the stream function first before we could use the idea of Navier-Stokes equation. So then, why we need to start with this? Because this is the only way for us to calibrate, to validate our equation whether it is true or not. Okay, because the stream function can be, the streamline here can be conducted in experimental works. So means that when we have mathematical equation for this line, we could compare with the experimental works. Then we could know that the equation is correct or not. Okay, so that's why we should start with the streamline. And as I said previously, streamline here is based from the actual thing, which is the flow rate, means the volume of fluid that move from one point to another point. because we want to make sure that our calculation is correct. Okay, this is another usage of a flow line, and this is the okay. Another thing, okay, another thing here. Okay, so we have problem actually. Okay, we have a problem if we only have this line only, because the idea of calculation is proposed, okay, in general is something like that. Okay, so let's say we have an aerofoil here, and then we have a line, okay, and then we have one line here, okay. So it is not easy for us to make a calculation because we have a long area here, because we just only have a streamline. A streamline mean a line, okay, from left to the right only. Okay, so it is not accurate to calculate that. So it is better for us to have something like this. Okay, it is good for us to have, for example, we have a streamline like this, and then we could divide it into a small pieces. Okay, because we could calculate, the idea is, okay, for example, we could calculate this one, and then because we have a 4 nodes here, we have a 4 point here. So, and then after certain time, we could calculate the movement of this area into this area. And then after certain time, we could calculate into this area to this area, and so on and so forth. Okay. So, and then okay. So the idea to calculate it in a very general idea is, okay. Okay, for example, we have an aerofoil here. So I draw the larger one. So this is the streamline, and then okay, this is not might be my drawing is not so good, so I change my object into a box, for example. So let's say we have a circle, and this is the flow line, the streamline, for example, and then we have a streamline like this. Okay, so first, for example, if we have one box here, so because we believe that the mass is constant, mass cannot be destroyed, so it just change and so on. So, and then we could draw another block here, which is will have the same mass from the previous block. And then we could draw another block here. In here, we could draw another block here, depending on the mass of the previous block. So might be because we have a longer here, might be we could write like, we could draw like this. And then here, we could draw another shape. Might be we could draw longer shape here, because to make sure that conservation of mass will be preserved. Okay, so and then again, and then at here, we keep drawing the same block as the beginning like this, at the start one, because the mass is constant. So mass is constant. Okay, so the idea is, but okay, because we try to use this idea, that's why we feel that the line here only is not so good. So we need to add another vertical line to help us in calculating, in our calculation. So if you do simulation previously, for sure you need to have 4 dots, to make sure that you have nodes that can help you to calculate something. So you cannot use you cannot start your calculation by having only these 2 lines. Okay, that's why to meet this purpose, we means the scientist previously. Okay, the scientist previously will give you the to calculate the idea of phi, velocity potential. Okay, but before that, I need to explain this one because I get why we have a velocity potential here. Okay, so okay. Okay, and then okay, actually our purpose is to know about the potential velocity. Okay, the potential velocity is actually if you draw a line with the equation of velocity potential, it will give you a vertical line like this. Yeah, a vertical line of this one. So I mean it will create a vertical line in here and so on and so forth. So finally your your situation you will have a lot of vertical and horizontal line. So it will help you to calculate very well. So might be at the beginning you will have a straight line, and then the line will keep bending depend on the situation and so on and so forth. Okay, so to draw that line, we will draw according to the streamline. Okay, but before that, we will see the theoretical or the main idea of the potential velocity. So what? So first, we are now. I would like to introduce you about the circulation. So the circulation is when we calculate when we analyze a particle which is moved in rotations. So so it can be considered, as I write here, as the amount of force that push along a closed boundary or path. In the other words, circulation is the total push, mean the total force you get when going along a path, such as a circle. So, and then, so the idea is, if you see the symbol is, it's written as gamma, is the circulation, and gamma is the idea is you need to multiply the velocity and the length of the distance that travel by the molecule. Okay, that's the common idea. Okay. So because the length of a certain molecule is actually it's not the absolute unit to define the strength of that situation. So scientists propose another term which called vorticity. So it's written as zeta. So and its equation is circulation gamma divided by the area. So what is vorticity? Okay, means is it is the tendency for element of the fluid to spin. Okay, so we do the calculation here. Okay, let's say this is for the Cartesian coordinate. So we have a 4 dots here. So dot here means that you just assume that we have a fluid flow from left to right on this path, and then another fluid flow on this path, and so on and so forth. Okay, so and then for one molecule here, okay, the fluid will flow to this one in u direction, in u velocity, and they also have component, means that if the molecule moves in y direction, they will have v velocity. And then for molecule here, so we'll have u plus du. Okay, and for the molecule here, it might be have v plus dv. So the word plus dv here, it might be it is equal to 0. dv is equal to 0, or dv will change, because this is actually the idea when we have a lot of molecules. So we just assume that if one molecule here travel from here to here and then go up and go left and then it backs to its location. So because it moved in circulation, mean in one circle, so we assume that the motion of this fluid is now actually more that it has circulation. Okay, so the idea of circulation is we multiply the velocity here with the idea of circulation here is we multiply the u, the velocity, with the length. Okay, so actually it is not a length. So in some textbook they will describe as it multiply with length and width of the path. So because we assume, just to make it shorter, to make it simple, we assume that the width of this path is equal to 1. So now means the area is actually dy times 1. Okay, then the gamma is the total force that push this molecule to move from here to here and go around and come back to the original location. So we calculate all the gamma along its path. So for this situation, it is u times the dx. So we have u times dx. And the width of this path is might be equal to 1. So we remain as dx. And then here, so it's moved from here to here in positive direction. So we have positive v plus dv, and the length here is dy times 1. So we write as d1. And for this one, actually the molecule will resist the velocity here. So we have the negative velocity minus u plus du dx, again because this the length is dx plus 1. And for this area, so it will become minus v times dy. So if we simplified all of this term, we could have gamma is equal dv dy minus du dx. So and then to get the zeta, to get the vorticity, so we divide by its own area. So we divide by dx times dy. So and then we could have zeta is equal dv over dx minus du over dy. And this is the circulation and vorticity in polar coordinates. So again, so we have this shape, and you know that this shape is actually come from the rotational, the movement of fluid in circular motion. So we have a u theta here and u theta plus du theta. So we have ur here and ur plus dur here. So and we assume that there is a molecule move from here to here and then come back to its original location. So we could calculate by using the same idea. So let's say for this one is ur times dr, and then the width is equal to 1. And then here is u plus du theta, and then the length here is r plus dr d theta. And then for this one is minus ur dur, and then we multiply with dr, the path of this one, and negative u theta r d theta. So if you simplify solve this one, so you will get this equation, and then we could calculate the zeta. The vorticity is gamma over area, so you will have this one. So why this is very important? Because we could determine the behavior of molecule that flow in certain fluid flow. So because in continuity equation, we need to have equal to 0, because we need to preserve or conserve to make sure that the mass is conserved. So the conservation of mass must be fulfilled. If not, your equation cannot be used. Okay, but for the vorticity, it is not necessarily equal to 0, because if zeta equal to 0, so we assume it is irrotational flow, means the molecule is not rotate itself. But if zeta is equal to 0, zeta is equal to 0, it is irrotational flow. If zeta is not equal to 0, it is a rotational flow. So means that the molecule itself will rotate. So the idea of rotational and irrotational, so it will become something like this. Because, for example, if our molecule is moving from left to right, and at the same time the molecule is rotate itself like this, so we call this one as rotational flow. And for this one, if the molecule is moving from left to the right, so and the molecule is static like this, not rotate, so it is irrotational flow. So in normally we assume in common calculation, we assume that all our calculation is actually irrotational flow region. Okay, because why it is not easy to calculate the rotational flow, because another phenomenon exists, which is the boundary layer. So the boundary layer will create no slip condition, means the molecule will stick on the surface here, and then this, you just imagine there is one stop molecule that not moving here, and molecule that interact with a molecule that stop that stick on the surface here might be rotate itself. So mean because it stick very hard at the bottom, but at the top here the molecule could push it into the flow direction. So might be it's could rotate. Okay. So at this condition, might be fluid particle could stay at this situation because all of this particle will move at same rhythm, means same strength. They don't create any uneven stress distribution. Okay, so we now going to have the fee here. So the fee here, it is the idea is the same. So the idea is the velocity times the distance traveled by the fluid. Okay, so because it is referred to the idea of circulation and vorticity. So circulation is about the velocity times the travel by the fluid, distance traveled by the fluid. So we want to have a velocity here. So, and the velocity can be written as the phi divided by the distance traveled by the fluid. Okay. So how to derive phi in computational? So we just use the idea of this one. So means we have a just one square box here to reflect our small particle of fluid. So we have u, we have v, and we have the length is dx and dy here. So we could say that u here is the d phi over dx. So from where we could get this one, because we take the definition of phi is equal to velocity times distance traveled by the fluid. So the velocity will become phi divided by the distance. So and then for here, u is equal d phi divided by the distance it travel. So means the distance is now dx. And then v is d phi divided by the dy. Okay. For potential velocity, for phi, there are no negative or positive, because the purpose of this line is actually to give you a vertical line to fulfill to help stream function and we could use that one for further calculation. So please remember that for velocity potential, there are no negative and they are always positive. And this is for polar coordinate. So we have this diagram. I hope you could understand this one. And then we could have UR is equal d phi over dr, and U theta is equal to d phi divided by r d theta. Okay, so if you write, if you could see that, so it will create a streamline like this. Okay, let's say this is the streamline. Okay, and normally when you draw a streamline, you will put an arrow mark because it's showing that the flow is from left to right or top to the bottom and so on and so forth. So, and if you draw a potential line, normally we are drawing a line without any arrows, because potential line is actually just to divide them into a certain cubicle like this, because it will help us to calculate the conservation of mass inside this mesh. That's why the basic idea of calculation. So this is another one. So this is the flow, the streamline, for example, and then we have phi, the vertical line, and so on and so forth. So might be we have a small line here because first we will maintain the mass, and then the mass might need to fulfill the idea of continuity equation. Might be the mass, the area is here is small, but might be the velocity is high. So the small area and the higher velocity will give you certain amount of flow rate, and for this area is, so might be the large area here, so the velocity will slower. So means that the continuity equation is keep the same for each mesh. Okay, that's the basic idea of the existence of phi in the calculation. Okay, and then another. Okay, then I would like to propose Cauchy-Riemann equation. Okay, and then the Cauchy-Riemann equation is because if you see in the Cartesian coordinates, so we have u that to describe the psi, we have 4 of them, and we have 2 of them. So, and then for polar coordinate, we also have u to describe the psi here. And then we have another u to describe the idea of phi for both Cartesian coordinate and polar coordinates. And this idea is actually proposed by the Agustin Cauchy and Bernard Riemann. So that's why we call this idea, this compilation of equation, as Cauchy-Riemann equation. So so it is about the combination of u equal d psi over dy equal d phi dx, and v is minus d psi dx equal to d phi dy, and so on and so forth. But the most important is, please make sure that when you describe about v here and psi, so you need to use the negative sign. Okay. So this is the usage. I think I will go. I think I will leave this one into the tutorial. Okay. I will upload it as a tutorial, and I hope you could understand this. You could make a revision of this one. So this is a very simple one. So, and then I would like to show you, because I aim to have the flow around cylinder, because one of our question, they will use the idea of flow in cylinder. Okay, so I will leave bypass the tutorial. So we have go for the usage of that ideal flow. So actually we are want to develop equation for flow around cylinder. But before that, I would like to introduce you 4 basic flow. So you could get this from any textbooks. Okay, yeah. Okay. Okay. Yeah, in vertical. Okay. So first, I would like to introduce the linear or uniform flow. So if you have one molecule here, move from this point to this point. So means that yeah, the stream function is actually the resultant stream function is this one. And if we distribute it into x and y, so it will become a stream function for x and stream function for y. So as you know, stream function is actually telling you about the flow rate. So flow rate is a scalar, means scalar we cannot sum them, add all of them by using the idea of vector. So if vector, might be we could calculate it by using the idea of hypotenuse and so on and so forth. But for scalar, so we just add them. That's why the total psi for linear here is actually the sum of stream function at y plus the stream function at x plus the stream function at y. So we just total them up, and then we could say that the stream function for linear here is uy minus vx. Why? How we could have this equation? Because the velocity is u, and then the cross sectional here is y. So we have uy, and v is from top to bottom, from bottom to the top. So it has negative sign, so it will become negative v, and it's the cross sectional here is x times y at x times 1 unit. So it will become minus vx. So and then if we want to convert this equation into the polar coordinate, we could write as uy minus vx, and then we could, by using this idea, for example, we have one center point here, origin here, so we have an r here, and this is the theta, and for sure this length is y and this length is an x. So the relation between x and y can be written as y is equal to r sine theta and x is equal to r cos theta. So and then okay, normally we will assume that the linear flow is parallel to x axis. So means this is the idea is, for example, in real situation, the water flow from this point to this point with certain angle. So might be you as person who want to simulate the flow. So why not you just take the direction of the water flow there is actually parallel with x axis. Means you just rotate your x axis here to make sure that it will become like this. So mean the x axis is parallel with the flow. That's why normally fluid mechanics people do, because it will simplifies the terms of v here, because it's now parallel with x axis. There are no velocity on y axis, so the term of minus vx will become 0. And then we could assume that stream function for linear flow is equal to ur times sine theta. So and then this is the simple one. So for phi for linear is phi for x plus phi for y. So we have ux, because u is the velocity for x, and x here is the distance traveled by the u, and plus Vy, because there are no negative or positive for velocity, potential velocity. So velocity potential. So if we want to write the equation by using the polar coordinates, so this is the equation, and then as I said, normally we have flow that parallel with x-axis, so it can be simplified as phi for linear is ur times cos theta. Okay, so this is the about another. We have a four terms that we need to use, which is a linear source and linear source, sink, and vortex. So it is source. Source, it is something that flow from one single point, and its flow according to the radial direction. So you just imagine you have a water source here, and the water will flow according to its radial direction. So means that the only velocity that occur at this point is ur, mean the velocity at r axis. So and for source here, for sure the water that comes out from this source will come at certain strength. So we call that is m, mean the strength of source. So, and then we need to calculate what is the stream function for this one. So the stream function is actually reflect the flow rate. Okay, because the flow is moving at radial direction here, so means that the cross-sectional area is actually the perimeter of the circle here. So and then the volume flow rate is the UR can be calculated as the volume flow rate divided by the area. So and then we could write as m over 2 pi r, and then it will have d psi over r d theta. And then we assume that u theta will be equal to 0 because there are no velocity that rotates that move along the theta axis. Okay, so let's say we could from this equation, for example, so we know that ur is equal m over 2 pi r, and from the Cauchy-Riemann equation we know that d psi over r d theta, and then we take this term and then we solve it, because our purpose is to get what is the psi, mean the psi for the source. So you know we have the differential terms here. So what we need to do, something, and then we will integrate both of the terms to get the final answer. So what we do is we just bring the r and d theta to the right hand side here. So we simplify it. So and then we integrate both parts, and then we could get psi is equal m theta over 2 pi. So it is okay for us to know that psi is for source is equal to m theta over 2 pi. So and this is I hope you could snap these notes. So the phi for source is m over 2 pi ln r. So it's depend on the same calculation, and the integral of this one will give you ln r. And then for sink, so for sink is the reverse phenomenon of source. If source, the water will come from one single point and move outside parallel with the radial direction. But for sink is water for the radial, for the outside, will flow into one single point here, will suck or will flow down into one single point here. So the velocity is actually negative UR, the negative direction for the source. And again, the cross-sectional area of this situation, of this phenomenon can be shown as 2 pi r. And again, the force of suction here will reflect the strength of the sink. How strong is the hole to suck that water. So we assume that the M here is the strength of sink, and then we could calculate negative UR is equal M over 2 pi R, which is equal to d psi over R d theta. And finally, we could solve this one. Okay, we use the same idea. Okay, you just bring everything R d theta to the left, and then you integrate all of them, and then you will get psi for sink, means stream function for sink is equal to negative m theta over 2 pi, means that it carries a same stream function, but the sign is negative because the direction of flow is actually from the outside to the center. The source is about from the center to the outside. And this is the, if you do the same things, you will get the phi for sink is minus m over 2 pi ln r. Okay, this is the vortex. Okay. Okay, because we have a polar coordinate and so on and so forth. So, and the nature of fluid is sometimes fluid rotate at certain area, like tornadoes, or we have a vortex and so on and so forth. So we have situation of one molecule here rotates on the circular path like this. Okay, on this situation, we assume that there are no velocity of r here, because if the velocity of r exists, the molecule here will rotate larger and larger because there are increment of radius. So because the molecule here will rotate at the same radius all the time, so we assume that the velocity is only u theta. And then because it is counterclockwise, and then we assume that we have a negative sign here. Okay, it is okay. Not okay. Okay, so for this one, okay, I just neglect the negative sign because we are going to evaluate it by using the idea of vorticity. No, the rotational. Okay, the idea of circulation. Okay, I'm sorry. Okay, so because it's rotates like this, so we use the idea of circulation, which is u times the distance traveled by the molecule. So the distance traveled by the molecule here is 2 pi r. So, and then we could rewrite u theta is equal gamma over 2 pi r, and then it is equal of minus d psi over dr. And then what we need to do is we integrate both side, and then we will get psi equal minus gamma over 2 pi ln r plus c, because the gamma here, the integration need to comes with the constant. So, and then we substitute the value of r equal a and psi equal 0. So why we put this one? Because in rotational movement like this, okay, so it's for sure it has constant radius, so it cannot have r equal to 0. So for this one, okay, we just assume that it will rotate at certain radius, and we assume that the the psi is equal to 0. So then we substitute the value. So we substitute the 0 here. We substitute the value of r equal a in the equation, and then we could say that c is equal gamma over 2 pi ln a. And then we substitute the value of c in the equation, which is the this equation, we substitute the value of C, and finally we could have the psi for the vortex is equal minus gamma over 2 pi ln r over A. So please, at least now, and then this is the phi. Okay, you could do this by yourself, I think. So, and then we have phi vortex. So normally people will focus on the derivation of psi. Okay, so here means that you already know these 4 types of flow. So you have a linear, source, sink, and vortex, and each of them will have their own psi. So we have a psi for linear, we have psi for source, psi for sink, and psi for vortex. So and then we will use this in our further calculation.